Welcome to our little Cross-Learning Alliance presentation here. My name is Matt Brady. I'm a mechanical engineer, senior associate with Syska Hennessy Group in New York City.
And my name is Maxwell, Hatfield, Biondo, senior associate, Jarrell Bauman Bowles, and we're happy to be here today.
The learning objectives for this class talk about refrigeration in everyday life, talk about basic refrigeration physics, then talk through the refrigeration cycle in a little more depth, kind of work our way through it, and then talk about the concept of a heat pump, how a heat pump is a little different from a refrigeration cycle, and some advantages associated with those differences. And then we'll talk in a lot more detail about refrigerants, legislation, and electrification, and how heat pumps are part of electrification. So, introduction to refrigeration. So everybody in this course, not everybody is a mechanical engineer, but everybody deals with refrigeration. You know, at home you have a fridge. At this point, most people have air conditioning in their home based on warm summers. So this is stuff we work with every day. It's not scary. It's not super complicated, but it does offer some really important advantages for our future. So this is the basic Carnot refrigeration cycle, named after the original scientist. So there's 4 pieces of the puzzle for refrigeration. You have an evaporator, a compressor, a condenser, and an expansion device of some kind. Those can vary greatly in complexity. Some of them are just an orifice. Some of them are a very, computer-controlled valve. And then the idea of it is that you're moving heat rather than creating it. So the first law of thermodynamics is that energy and heat cannot be created or destroyed, but they can be moved. So the second law of thermodynamics is heat always flows from a higher temperature to a lower temperature. This is the idea of entropy. Everything moves towards the room temperature, basically. So a refrigeration system is a way of sort of cheating entropy and moving heat against the flow from a lower temperature area to a higher temperature area. But because physics always wins, what you're doing is you're putting work in, you're putting electricity in to move the heat upriver. So normal heat transfer processes do all play a part into this. Those would be conduction, convection, radiation, and evaporation. So conduction is you touch the pan on the stove and the handle is hot. That's conduction. Convection is you're boiling rice on the stove and there's this movement of air over the stove, and as the air circulates in your kitchen, that's convection. Radiation is you, like me, picked up a pandemic habit. You got into baking bread, and you've got a cast iron crock pot in your oven that has the bread in it, and you can feel the shine from the cast iron pot when you set it on top of your stove after it comes out of the oven. It's not air movement, you're feeling the shine of the steel. And then the last is evaporation. Go back to the idea of the pot of rice. You boil water, and that water, you've put heat into it, you've evaporated it. That took heat from the stove and put it into the water. So types of heat: sensible and latent heat. So sensible heat is the most straightforward kind of heat. In a silly way, this is heat that feels hot. So this is heat that raises dry bulb temperature. So a light bulb, a computer, the sun, beating down on pavement, that's a form of sensible heat. The next form of heat is latent heat. Latent heat is a little harder to see. Latent heat is a measure of moisture. And the two of them together are the amount of energy in the air. So latent heat in this case has to be removed by the air conditioning system. So for cooling, you can imagine straightforwardly, you cool the air, it gets colder. But as it gets colder, it goes towards its dew point. And what happens on an air conditioning unit coil is the same thing as a glass, full of iced tea on a summer day. You get dew on the sides of the glass. So that'll happen on the coil, and then we pump that water that we've now created out of the system, and so now it's not in the room. So back at home, we go to our refrigerator. So refrigerator is the same refrigeration cycle as a large commercial building. So it works its way through in steps. So the first step is our refrigerator has walls that are not perfectly insulated, or it has a leaky door, right? So that's your heat source, is the heat coming into the refrigerator. raising the temperature inside. So once the temperature inside is raised a little bit, the refrigerant in the evaporator coil inside the fridge will boil. The refrigerant absorbs the heat from the food, from the leak in the door, boils. The next step, that refrigerant makes its way, having boiled, to the compressor. Compressor is like a pump for vapor, so it raises the pressure of the vapor and physically moves it from the evaporator to the condenser. And moving the fluid also moves the heat that was absorbed by boiling it. Step 4, that vapor goes into the condenser, rejects heat to the kitchen, and then it turns back to liquid. That's the condensing. It condenses. And then the next step is it reaches the expansion device. So after the compressor, it was at a high pressure. It's what allows it to condense in the kitchen, even though the kitchen is warmer than the fridge was where it boiled. So we're changing its properties by changing its pressure. The expansion device is just the pressure boundary that allows it to go back to the low pressure inside the fridge. So this is an example showing those liquid and vapor and pressure boundaries. In a house or a commercial building, frequently half of this system is outdoors and half of this system is indoors. So the condenser, we think of as being outdoors. Usually the compressor is outdoor with it. And then indoors, you have the evaporator and the pressure management device. So introduction to a heat pump. So a heat pump has all the same components, all 4 devices, but through some additional piping and a reversing valve, we can operate it in both directions. And so basically the reversing valve on the right, you take all the same components, you add a second expansion device, and now you have the ability to run the cycle, exactly the same cycle, but change which coil is the evaporator and which coil is the condenser, without physically moving them, because one is outside, one is inside. So now you can have the evaporator inside or the evaporator outside. So now this plays into this idea of coefficient of performance. So why is a heat pump important, right? So anybody that's lived in upstate New York has probably lived in a non-fossil fuel heated house, right? If you lived in upstate New York and you had electric baseboard, and you had Niagara Falls providing your electricity, there was no fossil fuel involved. But unfortunately, power in most of the country is not generated through hydroelectricity. So a boiler, we talk about COPs of 0.75, this idea that the energy you add compared to the energy you put in. Boilers have now gotten more efficient. There's condensing boilers at lower temperatures. You can get higher efficiencies. Electric resistance heat is, perfectly efficient, right? You put heat into the coil, that heat is in the room. But if you generate that electricity using a power plant, then the power plant efficiency affects the resistance, and it ends up actually, in some places, depending on the power plant, lower than the boiler. So the way that we get around this is by using the electricity in the heat pump, because the heat pump can move much more electricity than it uses in electricity to run the device. So a heat pump, we talk about COPs on the order of 2.5 or 3. And then we'll talk about the idea of heat recovery. And when you get the heat for free, the heat is waste heat that you would have otherwise paid to remove, then your efficiency can get extremely high, which means you need less electricity to do the system. So now what we end up with is a third pipe, and it's the same pieces, but we have multiple spaces together, each with their own coil, and then we have reversing valves that allow you to have the different spaces do different things. And so this way, instead of having to take the heat from outside or create the heat using a boiler, we can just take the heat from the hot room and put it in the cold room with just a little bit of electricity to move the fluid around. Okay, so first question, is a laptop computer an example of sensible or a latent heat source? Okay, the answer is sensible heat. Question 2, True or false, refrigerant changes phase while moving through the refrigeration cycle? And the answer is true. Question 3. True or false, a heat pump uses the same physical interior and exterior coils in both heating and cooling modes? Answer is true.
Thanks, Matt. So now that we have the basis of the refrigeration, the Carnot cycle understood, we're going to get in a little more into the application of how we apply refrigeration to building, design, and construction, and where we are now and where we need to move to in the future. And to begin that conversation, we talk about the actual fluid that Matt was talking about during most of the first few slides, and that is the refrigerant. Right. There are many different types of refrigerants out there that we can use as applied to the HVAC and refrigeration industry. But basically, the refrigerants are the fluid used for that as the medium for that heat transfer in any refrigeration system. ASHRAE Standard 34 is what designates the safety classifications of refrigerants. It's essentially the Bible of refrigerants, and every attribute about them all identified in standard form. Now, the designations that are applied to refrigerants basically are, there's a series, basically the organic compound they're made out of, methane, ethane, propane, for those more household names, and a number that is a designator more attributed to the chemical formula and the rest of the components. So when we see typical examples of what you may be familiar with, the R134As, that's a series and number designator for a particular refrigerant. Now, one of the first things you start talking about with refrigerants is the safety group classifications. And there are two main identifiers that we think about in terms of safety with refrigerants: the toxicity and the flammability. The toxicity, identified in class A or B, is basically how harmful or lethal is this refrigerant if it's exposed to an occupant in the event of a leak or a rupture of some sort of vessel. Basically, and this is measured in an exposure limit, an OEL, operational exposure limit, and the normal value is 400 ppm. So above or below 400 ppm is where we define how toxic a refrigerant is. Flammability is essentially the speed at which combustion and burning conflagration of flame of this refrigerant, again, when exposed outside of its containment vessel. And the higher the classification, the higher the number, the more flammable that is. And as a side note, here in our jurisdiction in New York City, the FDNY does not allow any refrigerant in any facility greater than an A1 rating. So that is the lowest no flame propagation value, is what the FDNY really limits us to utilizing inside our facilities. And what this means in real life is that there are plenty of refrigerants out there in terms of efficiency and how well they can do their job. However, they're a little too flammable to be around other occupants in these buildings, and therefore they're not allowed to be used. So we have to find other means and other efficient refrigerants and other combinations of components to make this all work. Besides the safety classifications, what makes up a refrigerant is their composition and different attributes. Then the high level items that we talk about are of their composition, and those organic compounds are these values here on the left: CFCs, HFCs, HCFCs, HFOs, HCFOs. It all has to do with what are the chemical compounds that make up the refrigerant. And what we want to highlight here is that through the Montreal Protocol and a lot of climate action plan and legislation, there is a purposeful effort to phase out some of these refrigerants that are harmful to the environment. And essentially, long story short, those identified as CFCs have been phased out. No new equipment can leave a factory floor and be shipped to a project with charged with this refrigerant. Doesn't mean that there isn't still equipment around today and still operating legally that have these refrigerants. However, no new equipment like this is being manufactured. And as you go down the list, they're, again, based on the different climate impact attributes of these refrigerants, there are phase out dates for some of these. Now, when we talk about what are the components of these refrigerants that we need to focus on, there are 4 or 5 main points we want to touch on here today. Ozone depletion potential, right? Degree to which that substance is going to degrade the ozone layer. This is measured against a similar mass of CFC11 or R11 as a way to normalize these values across all refrigerants. Another is global warming potential. And that's basically what it sounds like, right? The degree to which that greenhouse gas is going to be trapped in our atmosphere, right? And this is measured relative to a similar mass of CO2. That's the normalized refrigerant that we use for comparison's sake for all these. In addition to those two very important attributes, pressure classification is something us as consulting engineers and in the designers need to focus on. That has impact to equipment size, size of the actual refrigeration machinery based on the pressure it's going to be operating under. Atmospheric life is important, right? This is the duration that this refrigerant is going to stay captured in the atmosphere if it ever were to leak out of its vessel. And certain refrigerants will linger around longer and have more of a detrimental impact to the atmosphere. The point we'd like to make here too is that in terms of LEED compliance and any new construction projects, there is a LEED prerequisite, so it must be complied with before even attempting any LEED certification, and no CFCs can be provided in new equipment on the project. And if there are CFCs in existing projects that's seeking LEED accreditation, there must be a phase-out plan for the existing equipment. So let's talk a little bit more about, again, familiar refrigerants you may have heard of on projects and how it really applies to the buildings we're working on here. Kind of red, orange, green goes to show bad, better, best. But right, refrigerants in the real world, this day and age here in our jurisdiction that have been phased out, no longer allowed to be provided with a new equipment are things like R11 and R22, right? These are 15, 20 years old. They're still around. Like I mentioned previously, there may very well be equipment or facilities utilizing these refrigerants in place now and very well maintained, which is totally sufficient. But at some point, the existing refrigerant will be phased out, but there is certainly no new equipment being charged with this type of equipment, this type of refrigerant. Now in the transitional range, or refrigerants that we know do have a sunset for when we will not be able to buy new equipment in them, I've identified two of the more common ones that we see on projects all the time, R134A, R410A, right? Some of the jurisdictional requirements, legislation that I'll get to in a moment, have a sunset date of January 1st, 2024. So basically, manufacturers cannot ship any equipment charged with these two refrigerant, among others, can't leave the factory floor after January 1st, 2024, and they will have to be moving towards the next gen refrigerants, which are the lower rows here. So basically the next gens are really focusing on the global warming potential values. There are refrigerants that are blends of other refrigerants that are used as what we call drop-in replacements, where you can convert an old machine that's using some of the 4 refrigerants listed above and drop in a new with some impacts to the efficiency of that equipment. It may be derated in terms of capacity, but that's a very viable solution for building owners that need to comply with this changeover. And then there's really into the future, the ultra low GWPs, where we're looking into the future. That has really the best impact on the environment, among many more than just what's listed on these slides here. Now, to just touch on this briefly, right? The legislation and the codes that we need to think about when it comes to refrigeration here is the Montreal Protocol is the initial effort that was amended by the Kigali Amendment in 2017, but this all went into effect January 1st, 2019. So you can read up a lot on what this effort is bringing towards climate change, in particular as it pertains to refrigeration here. But in terms of Montreal Protocol, in addition, the federal government, the EPA, have policies in place that apply to everywhere in the country called the SNAP that basically lists approved refrigerants per use type. So we use refrigerants in air conditioning applications, cold food storage. There's many different industries that use refrigerants, but it breaks down what's approved per use type. We get it more and more focused in our jurisdiction here in New York, and we have the Department of Environmental Conservation, as well as in New York City, has Chapter 4 of our New York City Mechanical Code identifies refrigeration, specifically Table 1103.1, which is refrigeration data and safety classifications, which we touched on a few slides ago. And lastly, us as design professionals need to keep in mind that the Fire Department of New York, right, has limitations on what they allow in buildings based on the flammability limitations. So these are what we have on any given project to consider when it comes in the world of refrigeration. So to take a step back into how we're going to apply this to our projects, right? Matt introduced to us the heat pump concept a few slides ago here, but right, we were looking at the refrigerator example for our household device. We began to introduce what this means in terms of air conditioning a building, right? But a refrigerator is just a heat pump. And basically, heat pump is the refrigeration cycle operating in reverse, right? So through the reversing valve that we outlined here, that Carnot cycle spinning in the opposite direction allows us to heat, which is why these are called heat pumps. So we can heat and cool with these devices in a macro and micro scale when it comes to building design and construction. So a real life application of this, let's talk about your house. Many of you may have a split unit or have seen these in more residential applications where there's a condenser that sits outside rejecting its heat with its fan. And then there's another component on the wall up high where the cool air, the warm air is coming from, right? This is your heat pump, the two pieces with the refrigerant piping connecting between the two. And in the summertime, right, we like to think of air conditioning as the removal of heat from a space, right? The evaporator is removing the heat from the room in which you're keeping cool and rejecting that heat through the condenser, which is sitting outdoors. The same components stay there, sitting there. And with our reversing valve and our extra third pipe, we turn that piece of equipment in reverse and that will heat for us. It pulls the heat from the ambient air and puts it back into our building, right? So we think of heat sink, heat source, and moving heat from one place to another. That's really the big concept we want you to take away when discussing heat pumps. Now, a heat pump is a means in which to electrify buildings, but why are we talking about this at all? Why do we need to electrify buildings? There are four main drivers that are really pushing us to this conversation that, is at the forefront of our industry here, right? Number one, efficiency. It just simply takes less energy to move heat than it does to create heat. Matt introduced us to the first and second law of thermodynamics, right? It just takes less power. Instead of burning a fossil fuel to make that new energy, why don't we harness the energy we already have in place to move that heat transfer medium around? Number two, we have a very real law in New York City, Local Law 97, that has a carbon emission cap for all buildings in New York City. This is a reality, and the way to avoid these fines or the fees that are introduced if not in compliance is to electrify buildings. Another thing to keep in mind in this whole concept is the concept of drawdown. Right, and without reading the definition on the screen here, right, we're just trying to reduce the amount of greenhouse gases or compounds detrimental to the atmosphere. We have there be less of them in the atmosphere rather than more, right? And so the construction industry contributes to a lot of these refrigerants, a lot of these greenhouse gases in the country and in the world. And so we can begin to focus on drawdown by means of building electrification and focusing on the right type of refrigerant. And finally, a lot of this is hinging on the potential or the future need for our electric grid to become green. So Matt used the example of Niagara Falls in upstate New York, a little bit of a different scenario down here in New York City where our power comes from, right? But to electrify a building by not burning fossil fuels on site also means that we need our green to become grid as well, our grid to become green as well, right? We need renewable energy throughout. So when we electrify, we are minimizing fossil fuels across the board. So that was the why we're electrifying. Let's talk about how, right? So in any building, all year round, there are different needs in different thermal control zones for heating and cooling requirements. Now we're going to focus mostly on the wintertime because we're talking about electrifying buildings is really what's going to be the heat source. So we're going to mostly talk about the wintertime. But if it wasn't already known to you, there are air conditioning requirements throughout the year, even in the dead of winter. Of this theoretical floor plate here, the perimeter zone or the blue zone, in the wintertime, those spaces will need heat. They're right up against the perimeter glass to the different sources of heat transfer that Matt introduced. Right, there's conduction through that glass of it being very, very cold outside, and the occupants right on the inside of that glass need to feel warm. So those spaces will need heating. But the interior zones, that conference room and those storage rooms inside, have no idea what season it is. They have internal loads introducing heat to that space between the people, the equipment, and the lighting. And that heat needs to be removed from that space. So in traditional HVAC systems, you would take that heat and remove it from the space, but you would actually then be removing it from the building through the different various heat rejection systems of the building. What we're talking about now is, why not recapture that heat and use that heat that we're otherwise going to expel to the outdoors from the interior zones, and use that heat for the spaces that need heating, thus complying with that concept of it's more and always more energy efficient to move the heat than it is to create new heat. So that's the theoretical concept we're talking about with building electrification. How are we actually going to do that? All right, we do that with heat pumps, which is why we've been talking about heat pumps all morning. Now, there are two ways you can apply heat pumps to commercial construction projects, at this scale in large centralized configurations. We had the example with the sort of the residential split unit, which is exactly the same technology, or you can scale this up to something much larger. Centralized refrigeration machines, water source heat pumps, where the source of heat transfer is two different fluids, or air source heat pumps, where the source sink of the heat transfer on one side of the refrigeration process is the air, or the ambient air. So the air source heat pump is very similar to that split unit example with the house, all in one big package. So let's answer a few questions that we have in this topic. True or false? Are some refrigerants flammable? The answer to that question is true, right? And flammability is measured by classification. Question number 5. True or false? Only local codes have jurisdiction over what refrigerants may be used for air conditioning. The answer to that is false. We talked about federal regulations that have control over these limitations as well. Thank you for your time.